This computer. Okay, so let me continue this discussions. Give me a second. Okay. Okay. Now, yeah, I'm just talking about this. Okay, so in order to solve that problem, okay, so we just need to repeat what we did, and then we just need to guess some number, maybe D1 and D2 equal to 0, and then you can substitute it, and then you just keep looping the thing. So do you guys generally get the idea? Because otherwise I would just move on. Do you get the general idea right now? Okay, so otherwise we'll last until tomorrow 5 a.m. and then we may still talking about elasticity. Okay, so now the next thing is that I need to talk about is actually like just consider 1D system. Okay, and then there's a spring and then there's a body there or whatever. Okay. Now, and then I apply a force into that system, and then the spring is actually non-linear, so K is not constant, but depends on D itself. Okay. Sorry, or let me say it depends on X, and then X is actually the displacement. Okay. So let's say that I have a constitutive response that are actually X displacement, and then related to force, and that relationship happened to be nonlinear, but then you actually never get to the point where you get a flat line. So so we have a tangent that are actually K for a different X. So what we actually have is that df dx would be equals to kx, which is actually the stiffness, or actually more accurately tangential stiffness. Okay, is tangential stiffness because that stiffness only makes sense for given x. Okay, there is no one Bach modulus, one shear modulus. There are infinite of them. Okay, depends on what is your string, you get a different stiffness. Okay, so now how do we solve that problem? We need to linearizing it. The way to doing it is actually using using a discretizations method. So given this problem, okay, this is the exact problem without the Garman equations. Now I'm going to consider incremental state where I'm moving from here to here. I'm actually loading the material somewhere. And then let's consider that I have a Fn, which is actually the force at time equals to Tn, and then I need to find given Fn for given Xn, okay. And then we also know what is the increment of delta X or whatever. So find Fn plus 1 or vice versa. Okay, so how do we do it? Now we integrate these equations, and then we will have this equation df would be actually equals to xn plus 1, the integration of this. Okay. Now then the trick here is that I'm not going to solving the second term exactly, but I'm going to approximate it using the tangent. So I'm going to, instead of solving that nonlinear problem here, I'm going to linearizing this and then just consider this portion being linear. Okay, if this portion become linear, then this part will become k at x n plus 1 times delta x if I'm using a backward Euler. Backward implicit method. Okay, if I use explicit method, then k would be evaluated at xn, but then it would be less stable but you will get a linear problem. You see what I mean? Okay, but here I'm going to solving everything in a backward implicit manner. So this would simplify the system as a f n plus 1 equals to fn plus the k xn plus 1 delta x. Okay, this is actually also the Taylor expansions if you only consider the first term. Does that make sense? Okay, now what we need to do is simply solving the system. Okay, so now think about one thing. If I take a derivative again, what would happen? If I take a derivative of fxn plus 1, but this time on that derivative is respect to xn plus 1, then what I would have is that I would have k xn plus 1 plus k pi xn plus 1. So the derivative of k times delta x, right? You see what I mean? Delta x is actually xn minus x1. So delta x is actually xn plus 1 minus xn. Okay, so this is actually the thing that are actually interesting. This whole thing is actually called algorithmic stiffness. Okay, a lot of people ignoring this term, and if you ignore this term, you won't actually get the convergence to be quadratic, which is actually the Newton-Raphson's problem, because you're linearizing the system. Okay, now as delta x approaching 0, the discrete versions become identical to the continuum versions. Then f dfn plus 1, the derivative of this would be approaching the actual k xn plus 1, because this term is getting smaller and smaller. Okay, which means that if your delta is really large, then this additional algorithmic stiffness has to be considered. And I can tell you that most of my students ignore that second term. So I think that's why sometimes they implement a code and doesn't converge. So, okay, so systematic. I may need to cut what I'm saying because I think that my older graduate student, if they listen to it, may not be too happy about recommending them the skill, right? Anyway, so okay, so this is actually the material stiffness, and then there's a Rumfic stiffness. Okay, so far so good. Okay, so far so good. You still get it, right? Okay, now up to now, I never talk about anything about plasticity. Now I'm going to talk about a special case about the plasticity. That's the beginning of the plasticity. One necessary conditions of solving plasticity is that we need to able to solve a nonlinear system. Now after that, I need to define some new term. I will elucidate that idea using a bilinear system, and then I will using that opportunity to introduce some terminology, and then later on we're going to generalizing it in 3D. But then the 1D problem is actually easier to analyzing because in 1D you don't actually have anything. You don't actually have anything that actually require a lot of tensor calculus. Okay. So let's consider a 1D problem. In 1D, the material only have two mode. One is in tensile mode, one is in compaction. There is nothing. You cannot shear material in 1D, right? Okay, so how come we cannot shear material in 1D? In 1D. You can have extension and compaction, but that's it. Why is that?
I don't know, Professor.
Okay, so Jiayu, do you know why?
Um, well, I think uh, if you have a shear, it's going to be a 2D membrane problem.
At least 2D, it can be 3D as well, right? Why is that?
Right.
Because if you actually have shear, it changes the shape. So it's no longer 1D. The requirement to for something required to be 1D is that you can change the aspect ratio, but then you cannot actually literally changing the shape that are actually more than 1D in a more than 1D fractions. You see what I mean? Okay, so in 1D, you cannot actually have shear, but then so they only tensile and compaction mode. So let's consider a tensile mode so that we don't have buckling or anything that are funny. Okay, so there are multiple, and then assuming that the material can be linearizing it into a bilinear system. So if I have a stress and I have a strain, what happened is that initially I will have an elastic response, and then I will describe it using the 1D modulus E, which is actually have the same label of the Young's modulus, right? Okay, so at this point, I will have yielding. Okay, and then after yielding, what happened is that there are multiple possibility. One is that I will have hardening. Hardening meaning that if I look at the tangents of the hardening part, ET is actually greater than 0. Okay, so ET is the new modulus. Is actually the tangent modulus of the material. Okay. So beyond that point, I get degradations on that elasticity. Now I require a different amount of strain in order to change the same amount of stress. Okay, you see what I mean? Before, it doesn't matter. In the elastic regimes, if I want to change certain amount of stress, I need a fixed amount of strain because it's linear. Now that amount is different. It will still because the ET is degraded. Another possibility is actually have perfect plasticity that I will have a straight line. This is actually called perfect plasticity. Perfect plasticity means that ET equals to 0. Okay. Now another possibility is actually that I will have softening. So let me change the color again. Softening means something like this. Okay. Softening, then if you have perfect plasticity, ET equals to 0. If I have softening, ET is actually negative. Okay, which is actually interesting. I actually have more strength. Okay, I actually apply the material and then I increase the strength. Not only do I do not store more energy, I actually lost energy because of that more strength, right? Okay, this is actually the interesting about softening. If you have perfect plasticity, meaning that at the very beginning, I can store energy. How much energy do I store? So the energy that you store would be in that linear regions would be the string energy here before yielding would be equal to exactly 1/2 of epsilon E epsilon, right? Okay. After that, then I do not store everything. I actually have dissipations. Okay, so I lost part of the energy. Okay, but if I have softening, I not only do I store less energy, I actually lost energy from the dissipation that triggered the softening. Okay, and one thing that are actually very important is that in the linear regions, given a strain, you can get a stress, but here you cannot do that anymore. You see here, I have the same stress, but I have very different strain. Okay, so from the string alone, you cannot get the stress. You have to know where you are. You have to know that are you actually from yielding? What is this? So this become a time history dependent behavior. So how do we solve that problem? First of all, we actually need some additional tools. We were considering that the string itself can be partitioned into the elastic part and the plastic part. Okay, so how do I define that plastic part? It will be defined as the following. So this is actually the plastic string, epsilon p, and this would be the elastic string. And this would be the total string. Now, what happened is that I assume that the hardening mechanism is linear, then I'll have this, okay? But if I unknow the material, do it a little bit better. If I know the material, like this curve, so these two curves would be actually parallel to each other. They are both the elastic loading curve, whether it's loading or elastic loading or unloading, and then the slope of it will both be E. Okay, so which part is elastic, which part is plastic? This part would be the plastic string. And this part would be the elastic string. Okay, plastic string is actually the permanent deformations that the material will experience once you remove all the load. So imagine the generally of the stress underlying this curve. Okay, I increasing the strength. I actually imagine that you're seeing that experiment from the bar. I actually keep making it longer and longer until it starts to yield. After the material is yielding, I actually finding that for the same strength increment, I get less stress increment. Okay, and then at some point, I actually stop the loading. I actually unload the material. I unload it so much that eventually the stress equal to 0. But what I found out is that, okay, after the loading is actually removed, the material permanently become longer, right? How much longer? That length would be actually equals to the epsilon x divided by the L. Okay. Here I'm assuming that this is small deformation, so L and LO is actually equal to each other, right? Okay, but this is actually the permanent. So these portion is a permanent part. This one is the elastic part. Okay, so why do we need that? Because we are assuming that with that partitions, the stress is coming from the elastic part, which means that stress would be equal to epsilon, would be equal to the 1D modulus times the elastic loading, then that would be actually equals to the total string minus the plastic string part, and I will equals, and then that would be the stress. Okay, so far so good. Okay, now I'm going to take a time derivative of this whole thing, assuming that E is actually not sensitive to the time. Then I will have sigma dot equals to E times epsilon dot minus epsilon dot P. Okay. And then what would that equal to? That would actually equals to the ET times epsilon dot. Okay, ET is actually that tangential stiffness. Okay. Now, one thing that I want to introduce is what happened from here to here. Okay. So what does it happen? Now, this is actually called hardening, and what essentially happened is that when the material is yielding, you would actually reach the yielding stress. Okay. From here to here, the material is always yielding, which means that the stress is always equal to the yielding stress. Okay, but notice that yielding stress is here. So in order for the stress remain equal to the yielding stress has to be changed. And that change has to be the same amount of the stress. So the initial yielding is actually epsilon y0, and then up to this point, it would actually be the new yielding stress. Okay. So what happened is that if you consider the elastic regions, initially the elastic region is here. Okay, so I can actually have whatever stress, provided my stress is not hitting the yielding stress, I can actually have any loading here. Okay, sorry, maybe not any loading, sorry. I can actually load the material in whatever directions, but if whenever I unload it, it will go back to 0. If I actually remain in this region, right? You see what I mean? If the stress is actually never actually go beyond this, or in the compaction side go beyond this, I will have an elastic loading. Okay, do you get the idea? Now this is actually called these portions of the material. This one is actually called the elastic regions, and they are actually defined by this. In general, they're defined by stress. If they are defined by stress, it's called stress-based plasticity. 99% of the stress-based plasticity is actually defining the user yielding in terms of stress. Okay, including the undergrad Moore Coulomb criteria, they're actually stress-based. So what it means is that if I have a stress that are actually not bigger and not smaller than this initial yielding point, the response is not path dependent. Once you reach either the upper and lower limit, then this elastic region will change. And then it could change in multiple different ways. So here you're seeing that at the end of it, the yield surface is actually here, right? Okay, so there are two possibilities. One is that the entire elastic string is actually getting larger. Okay, so that is actually the new yielding stress. Okay. So that means now I need more tensile strength. I need more tensile stress for the next time I actually have the hardening. Or I can actually moving this. I can keep that the size of the elastic regions, and then I just moving it here. Okay, so this is actually a possibility too. Okay, so this is actually called kinematic hardening. And then the first one is called isotropic hardening. So hardening meaning that the change of the elastic regions for the material. So when I say region, it's not a physical region of X, Y, Z. Is that our mathematical model of plasticity is based on imagining the stress in Euclidean space. Okay, you see what I mean? In that case, is the Euclidean space is just one dimensions in the 1D problem. Okay, you see what I mean? Our theory is actually live in the Euclidean space that are actually defined by stress. So stress is the axis. Okay. So now I'll go back to this. Then what you actually would find out is that if I just pay attention on how this yield stress is changing, then I would actually have another set of equations. I would actually look at the strain, and then I look at how this initial yielding is actually changing as I actually accumulate more strain. Okay, so that slope is actually called the hardening modulus. And the OU stress would be, in that case, the new U stress would be equals to the OU stress plus the H pi times the epsilon P. Okay. Now, if I actually want to know how does this thing change, I would take a time derivative of it, then epsilon y dot would be actually equals to simply h prime epsilon dot p. Okay, you see what I mean? Because this one is the initial yield stress. It's actually doesn't change according to plastic strain. Okay, so this is actually h prime is actually called plastic modulus. Okay. Now, the next question is how does that plastic modulus related to the related to the tangent? Okay, so I will just do a very quick derivation here. H prime is actually equals to the change of the yield stress divided by the change of the plastic modulus approximately. And then this would be actually equal to the change of the stress itself times epsilon p beyond the yielding. Once it's yielding, you see, once it's yielding, then the stress is actually equal to, because when yielding, when the material is yielding, sigma equal to sigma y. Okay, you see what I mean? And then that would be actually equal to delta epsilon divided by delta E minus, sorry, delta sigma divided by delta epsilon P would be equals to delta epsilon minus delta epsilon E. And that would be actually equals to 1 divided by epsilon E epsilon sigma minus delta epsilon E divided by delta S stress. Okay, so that would be actually equals to 1 divided by ET, which is actually the tangent stiffness beyond yielding, divided by 1 divided by E. Okay, so do some algebra. So H prime is actually equals to H prime. Sorry. H prime is actually equals to ET divided by 1 minus ET divided by E. Okay, or another way to write it, ET would be actually equals to H prime divided by 1 plus H prime divided by E. Okay, so now I would actually formally define the plastic part. Okay, so the elastic regions of the material is actually defined as E, and that one is actually in 1D would be any stress that are actually a real number that are actually within the regions. Okay. Now, if I include the closure of it, of that boundary, then I would have the admissible stress. Space. Admissible stress space is actually equal to sigma. Again, will be being a real number, but then I would actually I would actually have a sigma y smaller or equal to sigma. Okay. Now, anything outside the admissible stress space is not physically possible. Okay. This is the big difference between elastic material and plastic material. For elastic material, if the tangent remain positive definite, you can imagine if in theory you can get any stress. There is no upper bound for stress. Okay, if your tangent is positive definite, you can get any stress you want, provided that there is no no yielding. But now with the yielding, there are some stress that are just not possible. That impossible stress would be anything that are greater than the yielding. Okay, So you can think about it as a physical object. The elastic region is actually kind of like, imagine that how to say it? Imagine that you have a rubber band here, and then your stress is actually a point. Okay, so if I actually using a force, if I'm moving that ball, that steel ball inside the rubber band, and then I can make it bigger, I can make it smaller, but then that ball will remain in the upper band, in the rubber band, and then the point where the rubber band and the steel ball are touching are actually the yielding stress. Okay, so okay, does that make sense? So that rubber band is in an analog to an elastic string. Now, if I actually if at each time I'm moving that ball and then the U surface is actually changing the boundary, I can make it longer. But then now if I actually have elastic unloading, it would be like if I'm moving that ball inside that regions. Okay, when I actually moving the ball in whatever path inside that regions, I cannot move the U stress. The boundary will remain the same, right? That is actually because the material doesn't have path dependent. Until I actually hit another boundary and I pushing it, then the shape of it would change again. Okay, you get that idea of the elasticity and plasticity. Okay, so what happened for material that are elastic? An elastic material is actually an extreme case where that yielding stress is become infinite. So there's no memory. Okay, no permanent deformations. Okay, so I would actually define a formal thing about that. So that region is very important. That elastic regions and then the boundary are defining by the yield surface. Okay, so Napon, so in one example, you remember the Mock Coulomb criteria?
Yeah.
Mock Coulomb criteria is actually a yield surface. Okay, once it's yield, then the Mock Coulomb criteria has to be changing, then which means that your frictional angle could change or your cohesion can change in order to matching the stress. Okay. Now the yield functions. So this is actually so so another important concept here is actually the yield functions. Now in 1D, yield function is simply you can writing it as a function of stress and then the yielding stress, and then that would actually be equals to, for example, absolute value of the sigma minus sigma y smaller or equal to 0. Okay, does that make sense? Okay, so and then that corresponding to elastic region. So if the stress is actually smaller than sigma y but larger than minus sigma y, then the material is not considered yielding. Okay, so if it's not yielding, it still is the elastic material. Okay, if it's a linear elastic, that means I can still use the E to actually guess what is from the string to get the stress. Okay. Now, then I will rewrite that admissible stress space using the yield stress, using the yield functions. Then I can simplify our formulations. The admissible stress space is actually now can be defined as any stress that are actually a real number that are actually within that yield surface. Okay, so this is actually the 1D yield surface. Okay. So there are some extreme cases that I want to consider. So what happened for the strain and stress? Okay, so let's say I have a E, and then I have actually ET after the yielding, and this is actually the yielding point. So what would happen is that ET is actually equals to h prime divided by 1 plus h prime divided by E. And E is the Young's modulus, h prime is the hardening modulus. One interesting thing is that as h prime become infinite, ET is actually equals to E, is actually approaching E, which means that if the material can yield, but then in the case where you have infinite amount of hardening, you can just get the same curve as the initial E. You cannot get a Young's modulus. You cannot get the tangential stiffness that is stiffer than the elastic modulus. You understand what I'm saying? Even h if equals to infinite, you can just approaching this. Okay. However, there is also a lower limit as h prime is actually approaching minor E. Then something evil would happen. ET would be actually approaching minor infinite. What does that mean? Minor infinite. So minor infinite meaning that this thing would drop. So this is actually when ET equals to minor infinite, or actually approaching minor infinite. Okay, for example, brittle material, suddenly you have a fracture, and then that E. So there's an upper and lower limit about the E prime. So E prime cannot be smaller than the negative of the Young's modulus, and it can approach infinite. But then even if it approach infinite, ET would be actually cannot be actually higher than E. Okay, in other words, minor epsilon. So ET is bound by these two values. Okay. Okay, so you get the idea. So yeah, so far so good. Do you get the general idea? Okay, about what is a yield stress, what is the elastic regions, and what is hardening. So hardening meaning that your elastic region is changing, or hardening or softening. Okay, perfect plasticity meaning that your elastic region, despite of the fact that their plastic strength developed, is fixed. If it's fixed, it's perfect plasticity. If you're actually making it larger or actually moving it, then you get hardening. If the elastic region is shrinking, you get softening. Okay. Now I need to introduce more terminology. Okay. That could make things okay. So you may wonder, why do I need it for 1D? In 1D, you actually don't need something so complicated, but you will actually require that when you're actually solving a real problem that are actually in 3D. Now I want to actually decompose plastic strain as two things that are actually combined together. So I will let something called accumulate plastic strain called lambda dot is actually equals to the absolute value of the plastic strain, and that one is always greater than 0. Okay. Now epsilon p dot is actually equals to delta lambda if F is if the material is in tensile loading, and it will be equal to minor lambda dot if the stress is in compaction. Okay. Now, if you write it like that, then one thing that you can also do is that your yield surface can also be written as the absolute value minus the yield surface, which is actually equal to the sine of the stress times the stress itself minus the yield stress. Okay. Okay, the equivalent, right? Okay, so now one thing that are actually interesting. I will take the yield surface. I will take a partial derivative with respect to stress. What do I get? Okay, I will simply get the sign. Okay. And then that would be actually be plus 1 which is respond to the tension mode, and the -1 equals to the compassive mode. Compactions. Okay, so what does that mean? Why do I actually need to bother this? Okay, so what it means is that the gradient of the stress with respect to stress give you the mode of how the plastic strain is accumulated, because the total plastic strain increment is actually equals to the magnitude of the strain increment times the mole of the stress times the mole of the plastic strain that are actually accumulate. Okay, so this one give you magnitude, and then this one give you the plastic deformation mole. Okay, so okay, you see what I mean? Okay, you probably learn it from the string. If you decompose the string, you can actually get multiple different mode. You can get a volumetric mode, and then plus a directoric mode. Okay, so that actually corresponding to in 2D and 3D. This is no longer a sign, but corresponding to a mode shape. Okay. So this is actually called a flow rule, because it tells you how does the plastic deformation accumulate. Okay, in 1D, there is only two ways it can accumulate. Either it accumulate the plastic strain in the tensile mode or in the compaction mode. Okay. In 3D, there are more. In 2D, there are more. You can do shear, you can have torsion, you can have rubber, you can have way more rich mode. You probably don't have torsions for the classical continuum, but you will still have a different combination of volumetric mode and directoric mode. Okay. Okay, so and then another thing that so this is actually flow rule is actually related to how plastic deformation accumulate. Or actually how plastic deformations increase. Okay. Now then there's another terminology, it's called hardening law and softening law. A negative hardening is actually the softening. So sometimes people just say hardening law, but they may actually including the softening. In the 1D model, hardening and softening are actually not used to govern how the string accumulate, but used to actually control how does the yield criteria change and evolve given a certain plastic strain. So in this case, that would be simply this law. Okay, so I have a hardening modulus times that magnitude, and then I would actually have this. And then if you look at it, that would be simply equal to h prime times lambda dot. And lambda dot has a specific name, it's called plastic multiplier. All right. So if the stress is actually reducing, if the U surface is actually changes smaller than 0, then that would only happen if the hardening modulus is negative. In that case, then what actually happened is that the admissible stress state is shrinking. On the other hand, if the yielding is actually increasing, the yielding stress, then you have to have a hardening modulus greater than 0, and then the admissible stress space is actually expanding. Now there are a few one thing that I actually need to do in order to enforce the memory. Okay, if you don't do it incorrectly, remember that we want to write an algorithm that can do elastic plastic. And then when I unknow it, I need to make sure that it won't go here. That would be completely fair. I need to make sure that it go here, right? So how do I actually control the logic? How do I control the logic? How do I choose rather to go this here or here? Then that I need to introduce a constraint. And this is actually introduced from the linear programming. Okay, I need to introduce a certain conditions so that I can actually making sure the memory part, I actually make sure that I go here instead of going here. And then that would actually, I would actually use a table to illustrate this point. So I have an elastic response and I have a plastic response. And by definitions, lambda dot is always greater than or equal to 0, right? Okay, when is lambda dot equal to 0? So Jiayu, when does the lambda dot equal to 0?
It's elastic,
Yeah,
loading
exactly.
or unloading.
Exactly. It can be whole loading or unloading. Okay. So lambda dot equal to 0. When it's plastic, lambda dot greater than 0. Lambda dot would never smaller than 0. If it's smaller than 0, it violates the constitutive law as a modeling, or it would be thermodynamically not admissible. Now then, I would actually consider the yield surface. Okay, the yield surface can only be smaller. It could be anything that are actually smaller or equal to 0. Okay, so what happened is that if I put the stress into the into the yield functions and my yield function is smaller than 0, then it's elastic. Okay, so F smaller than 0 is actually elastic. When it's plastic, F remains 0 regardless of what is the new stress. Because whenever I have the new stress, the yield stress need to change accordingly so that F as a function of stress and yield stress remain equal to 0, remain 0. Okay. So F can never be greater than 0. Whenever F equal to 0, you need to have lambda dot greater than 0. And then these two things would actually represent a plastic yielding state. Okay, if I, on the other hand, if I want to keep an elastic response, there are two criteria I need to fulfill. Lambda dot has to remain 0 and F has to be remain smaller than 0. It could be very negative. It can be very close to 0. It doesn't matter. Now, if I consider this column and then I times lambda dot and F together, what do I get? What would I get? If I actually want to write the equation together out of it, what if I combine these two? I actually have a lambda dot F equal to 0. Okay, so this is actually in linear programming, you see it a lot. This is actually the additional constraint you use to enforce the memory to make sure that you're actually going for the right path. And this is actually called KKT conditions. So Karash, Kuhn, Tucker conditions. If you're in finance, you probably heard about it a lot. This is from the 1939 master thesis of Karash. And the rest is actually coming from 1951, the book Nonlinear Programming. Okay, so you can say before World War II, this thing doesn't even exist. Okay. Now this is actually I think this is actually the equation all plasticity model has to follow. Now then the last thing is actually the consistency equations. Now if you think about it, okay, so if I write the consistency equation now, and then if I take the time derivative of this guy, what will it happen? I will have a lambda dot of F of stress plus F times sigma y times lambda dot. I will take another derivative equal to 0. Okay, so so if F dot, because we know F dot is actually greater or equal to 0, then by definitions, my F is actually also equal to 0. Okay, whenever I have a yielding, F has U stress has to remain 0, right? U functions. So then this term vanish, and what I would have is that F dot is actually equal to 0. Okay, this is actually called consistency equations. So when you write a plasticity model, it becomes very simple. I just need to I just need a rules. I just need to combine my flow rule, my hardening law, and my consistency equations, and then I have 3 equations, and then I may have 3 unknown. The unknown could be lambda, could be the new stress here. Okay, and then also the my internal variable. I will have enough unknown. So the consistency condition meaning that if F is actually equal to 0, then it should remain 0. Until unloading. Okay, does that make sense? Okay. Now, I just want to make a summary of this thing. So a plasticity model have the following ingredient. Okay. First is actually that you need a elasticity model. Okay. That makes sense, right? because your stress is actually equals to E times the epsilon minus epsilon P. So without the elastic model, you cannot complete the entire formulations. The second thing is that you need a hardening and softening law. Okay. Which actually tell you how does the epsilon y go. So the first one give you the relationship between stress and the elastic strain. It doesn't tell you what happened for the plastic part, but then the second one gives you how does the yield stress is changing according to epsilon dot p, the absolute value of epsilon dot p. The third one is actually the flow rule or the plastic flow rule. It tell you the how does the plastic strength is accumulating in the combinations of the magnitude and the directions. Okay. And then of course you need the yield function itself. Okay, you need the initial yield functions. And then from that, we can actually involve anything in 1D. Okay, so far so good. So Jiayu, do you get the general idea?
Yeah.
Okay, Napang, do you get the general idea?
For the most part, yeah.
Okay, so I mean, we cannot do that much, but I mean, one day, what can we do? But anyway, so I think that even for 1D, I still need to. I mean, I think I still need to. I'm kind of tired, but but then I think that we still in 1D. So I don't know whether this is helpful, but do you guys at least get the general idea?
Mm-hmm.
Now for the 3D or actually for the general stress, the whole thing is actually in the analog, very similar to the Newton-Raphson for the one for the scalar and for the linear system. You just change everything from linear into from a scalar to into a linear algebra system, but then the ingredient is identical. Okay, you in 3D you still have a elasticity model, you still have a hardening rules, but then everything would be on a linear algebra, and your flow rule would still exist. That flow rule is still using the accumulated plastic string, but then your stress gradient respect to the U surface would be a second order tensor. So Napon, do you know what is a tensor?
I think it's like
Tensor is like a matrix, except that tensor can be matrix. Tensor can be represented by a matrix, but tensor is not a matrix. It can be represented by a matrix. Tensor is a generalized concept of vector that allow you to have magnitude, but instead of having one direction, you can have multiple directions. Okay, stress, for example, is a tensor because for the stress, okay, for stress, you have actually coming from two things. So if you actually think about the ingredient of the stress, there are force and their area, right? Okay, in your undergrad, your area is actually a scalar. In reality, this is actually not true. Both F and N have orientations because on a surface, you actually have a normal vector, and then that normal vector is obviously a vector, and you have a force that are also vectors. So how does that force hitting the surface? And then what is the would actually introduce two vector. And as a result, in order to represent the stress, you actually need to represent it in a matrix. And the reason you need to have the matrix is that there are two directions that are acting on the stress. One is where is the force, and then another direction is another thing is the orientation of the surface. Okay, so I can give you an example. If the force is applied here, and then your normal vector is here, okay, so then what you have is a pure compactions. But if I have a surface that I also have a normal direction, but then I hit the force here, then I would actually have a portion of it that are actually that are actually on the opposite direction of the normal vector. But then I will have a tangential part that are acting on the normal vector surface that will actually change. That would be different than if my normal vector is here, but I still have the same force that are applying here. Okay, so in order to represent that, then you need a second order tensor. So now your elasticity modulus in general is also not a scalar, but a fourth order tensor. Why? Because it's actually tangential stiffness is actually relating the strain to stress, and both are second order tensor. So in order to represent the relationship between them, you need a fourth order tensor. Now, what is actually the change of the tangent corresponding to strain? How many order do you get? You need a sixth order tensor, etc., etc. Okay. So tensor is actually a physical quality that with multiple magnitude and with multiple directions. Okay. The magnitude, roughly speaking, is related to the eigenvalues, and the direction is roughly speaking corresponding to the eigenvector. That is one way to view it, or you can decompose it in another way. Okay. Now here I don't have time to talk about all the thermodynamics stuff or blah blah blah. There are requirements for the flow rule, and there are requirements for the yield surface, and then there is a requirement for the elasticity model. You don't have time to talk about it, but I hope that I give you a crash course on the 1D plasticity. So Jiayu, do you get the idea so far? Okay, so
Yeah.
I mean, so okay. So maybe I can give you some general thing about the. So what do you think the 3D thing would actually look like? So in 3D, everything will be changing to your elasticity model with instead of this, I will write it as C double dot epsilon, and then that would be elasticity. Okay, so double dot mean the CIJKL epsilon KLE. So this is actually a fourth order. So the unit, we need to actually tell you what is tensor calculus, but we can actually go over that later. And then your U surface would be actually written in terms of the stress matrix or tensor will be still equal to 0. Your flow rule would actually be the plastic strain times lambda times the partial derivative of it with respect to the stress, but then this would be the stress gradient, which means that this is actually also a second order tensor. Okay, and then your hardening law that actually doesn't change that much. Everything is the same, the ingredient is the same, and then what you need to do in order to solve that problem is actually put a system of equation to it and then solve for lambda and then for the epsilon e. Okay, and then the rest of it is just algebra. How do you represent the stress? How do I representing the epsilon? There are multiple ways to do it. One way is to decompose the stress into volumetric portions. So stress is a matrix, but or tensor, but you can actually write this, and then you can have a directory part. So this one governing is actually the isotropic part. This is the directory part. And then from that, you can also have some simplifications, or stress can be written as sigma 1 times the eigenvector of the sigma 1 plus sigma 2 times eigenvector of the sigma 2 plus sigma 3 eigenvector of sigma 3. This is actually called spectral decompositions or spectral form of the stress. Okay, then there are lots of constitutive model are written in structure in in a spectral form. Okay. So I only teach you the plasticity. I don't have the time to teach the container mechanics. And quite frankly, I can perfectly qualify to teach the container mechanics, but then in that case, I would be a teaching professor and I would have no funding to do anything. So hopefully I can teach the container mechanics in the future, but right now this is only for plasticity. I need to cut this part because I think if I upload it or this record is actually getting out, I will get myself into trouble. So I need to be more careful about the wording. But so container mechanics, but I don't think we have time to talk about it. If I keep talking about it, it probably take 2 days nonstop, 48 hours. I probably can finish everything I know about container mechanics. I don't know that much, so 2 days may be enough. But I don't think that we have enough energy here. So does anyone? So don't worry about it, Napon. You don't need to know it. You just need to. I just want to give you a rough idea about what is plasticity.
Yeah.
Okay. Now do you get it?
Yep.
Okay. So there's the elastic model, and then it could become yielding. Anyway, then there are multiple parts of plasticity. There were Mises plasticity, critical state plasticity, crystal plasticity, polycrystal plasticity. I mean, this is actually everything that we will cover as a research group. So we deal with all kind of plasticity. Whoever give me money, I will come up with a plasticity model. So you can think about me as a function. So whenever there's a dollar sign giving to me, I output this. Okay. You see what I mean? So you can model the promotion case of a professor as a U service, if you know what I mean. You will know it later. What does that mean? But actually, I have that dream one day. When I was waiting for my promotions. I was thinking about Sigma 1, Sigma 2, Sigma 3 as some kind of teaching, research, and service to the university, and then I'm distressed trying to hit the U service. But then actually, when I getting closer to the yielding point, I found out that the U service is moving, and then I was dreaming, and then I tell my PhD advisor it's not possible. I mean, I'm still in the elastic regions. The U stress did not move, right? Right. Well, but then he told me that we're dealing with a tenure, we're not dealing with mechanics. So we set up the rules, not you. So we can do whatever we want. Okay. So anyway, it's just a stupid job. So forget about it. But yeah, for the tensor calculus part, I think that you need to have a good background on linear algebra and you need to have a good background in calculus, and then the two things bombed together would be tensor calculus, right? So, Jia, do you think so? Are you good at tensor calculus?
I think so.
I think so too. Yeah, I think you're pretty good at that. So, I mean, yeah, so maybe I just okay. So so Lampont, do you need a very quick thing? Maybe I could do a 20 minutes version of it.
Okay. Yeah.
Okay, so I actually probably so you can think about tensor calculus. I haven't prepared any notes, so I'll just do it on top of my head. Okay. So when you try to do tensor calculus, the important thing is actually remember that there are always two things: direction or mode, and then the magnitude. Okay. So the tensor calculus the first thing you need to deal with is actually the basic algebra. Now, if I have a stress, okay, stress can be represented as a matrix sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma the v1, sigma 3 2, sigma 3 3. Okay, so this cosine stress is actually symmetric. So that means these three are actually the same as these three, so you don't actually need to write it. Okay, so you just need to, so you have 6 degrees of freedom for the stress. Okay. Now, what are the common application in mechanics is that you have a dot product. So, for example, stress dot n. So, what does that giving to you? So, n will be a vector. Okay. Given a material that actually having some kind of stress, let's say I'm compressing it. Okay. Now I consider an interface. I just draw a straight line, and then I would actually have a normal vector. So that stress the material is experiencing times the what would be it? That would be called the Jackson's. Jackson sometimes written as T. So Jackson is a vector. It's a vector because it's actually it has a unit of the stress, but it's not a stress because it has a vector because it's only considering the tangential and normal force component as how does it affect the material in the normal and tangential direction or any other two orthogonal directions. Okay. Now, if I actually times n dot n, what I would have is actually I would have the normal stress. This is actually a scalar. Okay. So this is actually the normal stress. Normal stress is actually not a stress matrix, but the measure of how many normal force that material giving to me. So I have a stress here. Now I cut an interface, and then I would actually have a force vector. I would have a traction. That traction doesn't need to be normal to it, but I can always decompose it into the normal and the tangential direction. So this is actually a scalar. Now, this is actually the tensor written form. So in the unsigned notations, I will write sigma ij nj. And then here I will write ni sigma ij nj here. Okay. And then, and this is actually the same as this. But I just don't want to write the details. Okay. So this is actually more on the, yeah, so this is actually the basic operations. Now, then I also have another thing that are very common is that when I want to represent a quality, a tensor quality, I can sometimes use two vector to create a tensor, like something like this. Okay, what I mean is Ni Mj. Oh, jeez. And Nim Mj, and what it means is that let's say I and j are actually equal to 1 to 3. That means I have n1, m1, n1, m2, n1, m3 here, blah, blah, blah. So you know what I'm saying? This is actually how you create a matrix, is to lump this component together and then call so the index. Okay. Now so one thing is that this is actually called the tensor product. This is called the dot product. So whenever you have a dot product, you reduce the directions. And then there is also another thing is the cross product. Whenever you have a cross product, you actually remain the same rank, but then you change the index. And then another thing is the calculus part. Now, when you actually consider a scalar, you only have derivative. You can have total derivative. Or you have partial derivative, right? Now, considering a multi-dimensional space, then your derivative is you can actually have multiple different type of derivative that have different meaning. Divergence, gradient are actually the most common one. There are other things like curvature. That actually give you this divergence and gradient both give you the sense of how things change in a space, but they actually have different meaning. So if you have a divergence, so what it means is that if I have a divergence, it doesn't make sense to have a divergence on a scalar. If you have a scalar, then you have a divergence, it doesn't make sense. But for a vector, if I apply the divergence on a vector, what it actually means is that I want to measure the difference of the v with respect to the phi orthogonal basis of the space, and I want to add them together to give me a sense of how things change corresponding to the space. So in 2D, that would be equals to Vx plus Vy. Does that make sense? I just add everything together. Okay, so this one is a scalar. It's a scalar measure of how the vector change, and then I simply add it together. Okay, gradient is another type of operator where if I apply the gradient on V, so what would happen? If I apply the gradient on a scalar, let's say P, I would actually get a vector. So I would have a Px corresponding to the x directions plus Vpy corresponding to the y directions corresponding to the py's. Okay, so gradient actually gives you a sense of how things change in a vector sense, which means that, and then I will consider how things change in the how does the p change in the x directions as an x component of x, how things change in y, and then I will assign that magnitude into the y directions and this magnitude to the z directions. Okay, if I have a vector. If I have a vector and then I compute a gradient, what happens is that I would again get a tensor. So in the Einstein format, the divergence is written as Vi, comma I, and then the gradient versions would be gradient Ij. Okay, so one thing that you may notice is that in Einstein format, if you see the same index, the dimensions of your physical quality reduce. So V is a vector, right? But divergence of V is only a scalar. Okay, so here V is a vector, but the gradient of the V is actually a second order tensor. It's called second order tensor because there are 3 index. I can give you another example. If I have a string would have a 2 phi index because it's a matrix second order tensor. But if I take a derivative or stress is actually second order. But CIJKL, which is actually the stiffness matrix, is actually fourth order because this is actually equal to the stress partial derivative corresponding to the strength. Okay, and they will have 4 individual index, and then the reason is that you need to actually consider how all the stress change corresponding to all the strength changing, and then they are not, so that you increase the rank. Okay, so in one theory, one thing that actually in container mechanics, your goal is actually to mathematically rewriting something in XYZ in some in general, in a very general sense, you actually study or create a 3D objects in a Euclidean space or in a non-Euclidean space, and then you apply rules so that you can change that object or get a stress from that object or whatever. Those are actually the idea of the container mechanics. A sub branch of it is plasticity. Plasticity is to govern how does the history of the strength affecting the plasticity. And then in order to do that, you need an additional machinery, which is actually create a stress space. And then under in the stress space, this is actually where your plasticity theory live. So some combination of certain stress give you certain behavior. Okay. And your whole idea of running that, then you run things in the finite element, you can actually consider the finite element as a tools for you to actually also create another space that is spanned by your basis functions to actually so that is actually finite dimensional. Okay, you see what I mean? Anyway, I don't want to keep teaching different courses in every 10 minutes, but so not so, but then maybe I will do it still. So when you actually when you have a body and then you want to know how this thing deform, the only thing that the only information you already know is actually the gradient of stress has to be equal to 0 everywhere. Sorry, not the gradient, the divergence of the stress. Okay, so now in your finite elements, in the finite element, the basic concept is that instead of consider this without any idea how does the displacement look like, I will only constrain my displacement to be in certain way and in finite dimensional space. So that if U is in finite dimensional space, I can solve a system of equations. Anyway, so I don't know whether I give a very I don't think I'd actually do a very good job on giving the container mechanics lecture without any preparations, but I hope you get some really general idea. There are other things that I haven't talked about, and there are just too many things, like what is a chase operator? Okay, well, by the way, you should know what is a chase, right?
Yeah. I think you add up the cross term.
The diagonal together. What is
Yeah.
the determinant? Okay, you probably already know. So here what we need to do is that we need to know the meaning of this thing in container mechanics. So if you have a if you have a body that actually defined with x and have a position vector, if you deform it, that is actually got deformation gradient, and then your new coordinate is actually small x. F is actually equals to the mapping from x to the current x, the partial derivative of it, and then the determinant of the f is actually equals to Jacobian, which gives you the change of the size. How does this size corresponding to this size? Anyway, there's so many things that I want to talk, but then I think that I'm running low of energy, and I think so do you, right? So I just stop here. So okay. So if you forget anything, so if you forget everything, I think this is okay. Hopefully I can actually get the chance to teach your course again, and then okay. So yeah, I hope that get you a general idea. Okay, so tomorrow I think the interview would actually be okay. So I mean, okay, and I think that I need to find another time maybe to maybe Jiayu, I will probably find another time just to teaching you the plasticity course, and then Napan, you're actually welcome to actually attend the course. But I know that you're probably busy. How many courses are you taking right now?
I'm taking 5.
Okay, so I will spare you from listening to me. If you work with me as a PhD student, you probably have a tons of you probably listen to me mumbling all the time, right? Isn't it, Jiayu?
I don't think so.
Really? You think that you don't have enough FaceTime to meet with me?
Yeah.
You would rather talk to me every day? Okay, sure. I mean, be careful about what you wish for. Yeah. Yeah, sure. I mean, now why not? I think that I think we need to actually we probably need to find a way to make this thing work. So anyway, so maybe I will try to see whether I can find another time. So next week I'll have lecture 2. Okay. And then lecture 2 I will talk about what measures plasticity. And I will go with different type of plasticity, crystal plasticity, large deformation, blah blah, and I will go for it. Okay. All right. So thank you so much. So good luck, and then Napan. So have a good sleep, and then did they finalizing the meeting time already?
No, not yet.
All right. I will let them. I will let them decide whatever they want to do. They are the host. We are just the guests. So whatever they decide, I'll try to squeeze the time to work on that. Okay. So and Ajayu, thank you for attending this. Okay.
Thank
So,
you.
yeah, I mean, it's my job. So I hope that we can get a nature paper really soon, right? Or science.
I hope so.
Yeah. I mean, I hope I can get one before I pass away, but that would be my goal. So, but I mean, realistically, we can probably do something very soon. I think that I'm pretty sure, Jaju, by the end of this year, we'll have our first paper together. Okay.
Okay.
Maybe more than one. How many do you want?
I guess 2. One with Ryan and one with one about plasticity shear band.
Oh, okay. So yeah. I think that the paper we ran would not be that difficult. I think that the one with the machine learning thing would be actually more challenging, right?
Right.
Right. Yeah. Anyway, so let's call it a day right now, and then okay, and then I would see what happens. So good luck on everything. So and Napon, I'll talk to you and John tomorrow.
Okay.
Yeah. Okay. Thank you. Bye.
Thank you. Bye bye.